Alrighty, we're on section 4.2, quadratic equations. So we're going to be looking at different ways that you can solve quadratics. And remember, quadratics are the degree 2 polynomials, so parabolas. So looking at that. In section 4.1, we talked about sort of the easy ways to approach polynomial equations and solving. But today we're going to start talking about, just for degree 2, what are some other ways that might work if you are trying to solve? So other options that you have to solve those. So we're going to go through a bunch of them. So first order of business, when you look at solving a quadratic at degree 2, the easiest way to solve is if you solve it by factoring. That's what we did last week, or in the last lesson. So we did factoring to break things down when it was, I'm going to say, easy, nice numbers. Those solutions that are real, which is great. I mean, it works well if they're real solutions, but we know that they're not always. So how do we deal with it if it's not? Another way that people sometimes solve is they solve by graphing. So taking a look at the graphs and seeing the locations that would be the zeros or those x-intercept points. Again, if they're whole numbers, fabulous. But if they're, say, decimal numbers, or if they're imaginary, you wouldn't see them at all. So really not an awesome way to solve. Another way, going back to your advanced algebra days, complete the square. Another way that you can solve has to do with coming up with a polynomial that is perfect square and then square rooting both sides and solving, which is fine and it works really well. I think a lot of times people forget how to do that. I think we get down to our maybe our best possibility, which is the quadratic formula. That's that lovely x equals opposite of b thing. There's the Pop Goes the Weasel song that we'll be singing in class to help people remember it. So it's just a way to solve no matter what the solutions are. So for me, my first line of defense is if it's factorable, I'm going to try that. If it's not, or it's not easy to factor, I'm going to go straight to the quadratic formula, because that's a way that always works no matter what your solutions are, whether they're real, imaginary, rational, irrational, so nice or not nice, quadratic formula gets you there. All right, so let's go back and kind of take a look at what we were doing from before and just keep that perspective of sort of our 4 options in mind. When I look at these, I think about, are they good candidates for factoring? Because if they are, that's a really fast, quick, and easy way to do this. So this is a great candidate for factoring, right? I can multiply to get a negative 36 pretty easily, or you could just, oops, I say 36, and then I write it. You can multiply to get that 36 very easily, and we get our 2 solutions, x equals 6, x equals negative 6. This is a great candidate for factoring. I would never do this by quadratic formula because they're easy numbers. And remember what we were doing before, that means you can put your x-intercepts as your zeros or your solutions. Your y-intercept, remember, is always your constant, so not to scale, but we have at least a rough sketch of what that graph should look like. So this would not be one that I would consider using quadratic formula because it's just so quick and easy to do by factoring. Same thing for the next one. When I'm looking at things that multiply to 5 and add to 6, that's a really kind of quick whole number sort of answer when I look at multiplying those together. So I get my 2 solutions, negative 5, negative 1, so 2 real roots, and they're distinct again. So for both of these, there's 2 real solutions, and they are distinct. That means they cross in different places. Really good candidates for solving by factoring. So for this one, my zeros are at negative 5 and negative 1. My y-intercept is at 5. Let's talk about the vertex for a second for this one. The vertex is not a point that's obvious to me. The only thing I really know about it, I guess, is it has to be halfway between the zeros. And that would put me at, what, negative 3. And it's going to be down here somewhere. It's opening up, so I know it has to be below the x-axis. So I know its x value is negative 3. I don't really know where the height of it is, though, so I'm just going to approximate. And then another point that I know, if it's over 1 and up 5 from this 0, I have to have left 1 up 5 from that one. They're symmetric, right? So I can get a pretty decent sketch of what that parabola should look like as well. So just realize that if factoring works, great, do it. You don't have to solve by quadratic formula. All right, so what is the story on quadratic formula? When you have a degree 2, so this ax squared plus bx plus c equals 0 guy, you can solve to find the solutions, the zeros, the roots, by using this quadratic formula. This x equals opposite of b plus or minus square root of b squared minus 4ac all over 2a. If you remember singing it as Pop Goes the Weasel, it might help you. What are the a, the b, and the c? Those are just the coefficients of the terms in that quadratic. So A is always the leading coefficient, B is always the linear coefficient, C is always the constant. So when you look at the values that you get, just be careful, be aware, this part of it under the radical, the b squared minus 4ac part, is called the discriminant. So the part under the radical, that piece of it, not with the radical, but that piece underneath, that number, will help you determine the nature, we say, of the roots, the type of roots that you have. Are they real? Are they imaginary? How many do we have? All of that. So discriminant comes from the word discriminate, not a negative connotation. We're not talking about what it is in between people. We're talking about discriminating between roots. What type of solutions do you have? All right, so just a quick little review on the discriminant so you remember what we're dealing with there. So if it's greater than 0, that means positive. Can you take the square root of a positive number? Well, sure you can. When you take the square root of a positive number, you get 2 real distinct roots because it would be plus or minus. So we get 2 real roots. So 2 real distinct. You can take the square root of a positive, and that means for your graph then, your parabola must be crossing the x-axis in 2 places. So you would have 2 x-intercepts. So distinct means different locations. So if it's square root, plus or minus 2 different numbers, but you can take the square root of a real number. All right, let's take a look at the next one. What if it's 0? What if the discriminant is equal to 0? Well, if you go back and take a look at the quadratic formula, if this part is 0, square root of 0 is 0, you lose this entire part, would be 0, and you're just left with a single number, whatever that is. Well, if it's a single number, that means the graph is only touching in one place because it's a single number. So what kind of parabola would that have to be? What point would have to be on the x-axis? Well, it would have to be the vertex. And that's the kind that we call 2 real, but that root is a double. So it's counting as 2 separate solutions. So it just happens to be the same number. So there's 2 real, but they both happen to be the same thing. All right, then the last version is what happens if the discriminant, that number underneath, is negative. Well, can you take the square root of a negative and get a real number answer? No. So you're going to have 2 imaginary solutions. And what would the graph look like if it's imaginary? Well, that means you don't have any x-intercepts at all, which means your graph doesn't cross the x-axis at all. So looking at the discriminant really helps us make that determination. All right, so let's try a couple of these where we're going to look at what's happening to solve a quadratic. So make sure it's in standard form first, so it's equal to 0. So that's what we have here. Now, I guess for me, I would take a look and see if that's something that's reasonable to factor. 3 and 7 are not big numbers to deal with. They only have one option, 3 and 1, 7 and 1. The problem is when I think about the combinations of numbers, since they both are going to have to be negative, there's no way I'm going to get a -4. It's just not going to happen. So it's not going to be factorable. If you graph this on your calculator, you may want to pause the video, go ahead and type in 3x squared minus 4x plus 7 and see what the picture looks like. Look at the graph and see what's happening. It's really going to reinforce what happens when we do the quadratic formula. So I like to find the discriminant first so I know what I'm dealing with here. So let's figure out the b squared minus 4ac part because I don't think this is a great candidate for factoring. So the a, the b, and the c. The a value is going to be the 3. The b is going to be the -4, so with the sign, and then the c is the 7. So b squared would be -4 squared minus 4 times 3 times 7. I'm really going to encourage you to stop the video, try the arithmetic on your own to make sure you get the right number. The most common errors on this is dealing with the arithmetic underneath the radicals, so be careful. All right, so you should come up with -68, so double check and make sure. Now, what does that tell you? What does it mean? If you get a -68, well, that means you have 2 imaginary solutions. If my discriminant is negative, I'm going to have imaginary answers, so 2 imaginary solutions. So right away, I know this graph, when you looked at it, it should not have crossed the x-axis. There are no x-intercept points. All right, so let's use quadratic formula then to find those complete solutions. So x equals opposite of b. If b is -4, that means that would be +4, plus or minus the square root of -68 all over 2 times a, so that's 2 times 3, that would be 6. All right, let's deal with the 68 ones for a second here. So -68 square root, I would first of all break down like this, kind of do my scratch work off to the side, break it down into -1 times 68. So -1 would be your I, and then we can deal with the 68. So 68 isn't a perfect square, but see if you can figure out if there's a perfect square that divides into 68 evenly, and then we can break it down. So if it's 4 and 17, I know 17 can't be broken down more because it's prime. There's no perfect squares in there. So square root of 4 is 2i square root of 17. That's the order I like to put it in, the whole number first, and then the I, and then the radical. So 4 plus or minus 2i square root of 17 all over 6. All right, not much else we can do with these imaginaries other than reduce the fraction if we can. And if you look at all of the coefficients, if there's a common factor that appears in all of them, all three of them, we can reduce. And it looks like all of them have a factor of 2. So I'm going to divide everything by 2. So 2 plus or minus I square root of 17 all over 3. All right, so what does that give you then, really? The plus or minus is really a shortcut for writing these as separate solutions. So you have one with the addition and one with the subtraction. So really, technically, those two that I just wrote are the two solutions. It's totally fine, especially for these imaginary solutions, to write them in that plus or minus form, but realize those are the two answers that you get. So if you wanted to work backwards and write this, you could do the arithmetic that you need to here. So we can multiply these two horrible things together and do the arithmetic, and you would get back to x minus the root, multiply that together back to this blue box. We would get back to our original statement. So it's a way to find those solutions when factoring, quite honestly, just isn't going to do it. All right, let's try one more of those, then we'll get to an application. So again, when I look at a question like this, it kind of seems like it could be factorable. But if you think about it, are there any numbers that multiply to negative 12 that would add to negative 6? Go through the possibilities, 1 and 12, 2 and 6, 3 and 4, none of them work. So I know that this is not going to factor. So let's find the discriminant. I'm just abbreviating here. So b squared minus 4ac. All right, so the b squared, that would be negative 6 squared, minus 4 times a. What's our a value? Looks like that's a 1. And times c, that looks like it's a negative 12. All right, so go ahead, pause the video, do the arithmetic as you need to. And I got 84. All right, so what does that mean? What does that tell you? It's a real number, positive, so that means I'm going to have two real distinct roots. Distinct because it's going to be plus or minus that, so I'm going to get two real distinct. They're not going to be nice though. These are not going to be nice numbers because 84 is not a perfect square, but they'll be real for sure. So that means this graph is going to cross the x-axis how many times? 2 at 2 different places. All right, so let's figure out what those solutions are. So x equals opposite of b plus or minus square root of our discriminant, which was 84, all over 2 times a. Well, a is 1, so all over 2. All right, I'm going to do the same thing I did last time. Let's break down this 84. Not a perfect square itself, but what is a perfect square that divides into 84 evenly? So that would be 4 times 21. 21 can't be broken down any further because there are no perfect squares in 21. So I know that I've gone far enough, so that would be 2 square root of 21. So 6 plus or minus 2 square root of 21 all over 2. Alrighty, now let's think about this. I can reduce a little bit because everything has a common factor of 2 in it. So that would give me 3 plus or minus square root of 21. So you can reduce down to that. All right, now I'm going to write what those would be as separate solutions. We have 3 plus square root of 21 and 3 minus square root of 21. So you actually get two solutions. Now let's give a little reality check here. If you wanted to actually, in a real life situation, tell someone what these numbers were, if you walked up to someone and say, hey, the answer is 3 plus square root of 21, most people are probably going to look at you funny, like, well, what is that? So we can write these instead. Like if you go ahead and graph it, why don't you graph it on your calculator? X squared minus 6x minus 12. Look and see where this is graphed and where it's actually crossing, those decimal approximations, and then type these into your calculator and get a decimal equivalent for this square root of 21. I think you'll get a much better picture of what the numbers are going to be. First one's about 7.6. The other one's about negative 1.6. And that might be a much more reasonable way to say the answers to someone depending on what you're going to do with them. So realize you can actually figure them out as two separate solutions. If you look on your graph, it's crossing between 7 and 8, crossing between negative 1 and negative 2. So it's just a different way of writing the same thing. All right, I'm going to skip the next one for right now. If you want to practice it just as a little bit of extra practice for yourself for this next one, just to see, go ahead, pause the video. You can try it, and then I'm going to go ahead and write the answers. The discriminant for this one should have ended up to be negative 4, which means you're going to have two imaginary solutions. And my answers that I came up with would have been this. So you can double check and see if that works for you. All right, so I want to take a moment to talk about this application question, a place where people actually use parabolas. Basically, anytime you hit something, it goes up and it comes back down is a great example of a parabola. So in this case, we're talking about Mark McGwire of the St. Louis Cardinals. He broke a home run record a long time ago in 1998. Obviously, many people have since then. But this is an example for him where he hit the ball, did a pop fly, and it went up and then it came back down. Lots of home run hitters hit pop flies too. So the question is, and I underlined it in red for you, how long did the catcher have to get into position to catch the ball after it was hit? Another way of saying that is how long is the ball in the air? How long does it have before it hits the ground? And I want you to think about what we're doing right now. If the ball is hit and it goes up and it comes back down, how long until it hits the ground? That location is when the height of the ball is what? Well, if it hits the ground, it's at a y value of 0. So you're trying to find the 0 of the function. It's exactly the same as what we've been doing. So I have a little bit more detailed sketch here for you to take a look at. It says the ball is hit. It's not right at 0. If you take a look back into the description, what height was the ball hit from? Looks like 3.5. And if you look in the equation, you're going to see that right there too. That's your y-intercept. So why is it at 3.5 and it's not at 0? If you hit the ball at 0, what would that mean? Well, that would mean you hit the ball right on the ground. So that's not usually the kind of pitch you want to take, although I probably have taken a few of those. But you want to hit it from the height of where the ball was. So that's the 3.5 feet off the ground where the bat actually hit the ball. And it's going up. It reaches its maximum height, and then it comes back down and it hits the ground. Now this maximum height location, that's the vertex of the parabola. That's an absolute maximum point on your graph, and we're going to talk a little bit more about that in a minute. So we want to figure out the zeros. Now there are 2 zeros to this equation, right? Because there's 2 places where this parabola crosses the x-axis. The one that we want, though, that makes sense, is the one after it's been in the airfoil. This one looks like it's crossing before the y-axis, a negative time. So I know it has 2 solutions, but one only really makes sense for the domain of the function that we're talking about. Okay, so let's take a look at the equation. We're trying to find the 0. The height is 0. When does it hit the ground? Well, this is not a good candidate for factoring, right? You look at that, that's disgusting. We just want to use our quadratic formula to help us solve. So it's t equals now, because we're using t for time, but that's the same as x. So opposite of b, so ABC, plus or minus square root, I'm just going to put the discriminant underneath here. So b squared minus 4 times the a value times the c value, all over the entire thing, 2 times your a, which is negative 16. Okay, pause the video. I want you to figure out a number for this discriminant underneath. All right, so you should have gotten 6624. And we're going to go from here. All right, now again, in reality, if you're going to tell the catcher, all right, you're going to have to get over there in this amount of time, you're probably not going to say negative 80 plus or minus square root of 6624. You're probably not even going to want to say whatever 6624 is simplified as a radical. That's just not really easy and user-friendly. So we're going to go ahead and approximate this in decimal form so we can use it a little bit easier to talk to people. So it's more of a what are you using it for kind of thing. So square root of that number, I believe, is 81.4. And we're going to simplify. All right, so what are our 2 solutions? What are they coming from? Well, one time is going to come from taking negative 80 plus 81.4 over negative 32. The other time is going to come from taking negative 80 minus 81.4 all over negative 32. So we have a plus and a minus. Make sure you do the entire operation on the top first and then divide by the bottom. So just be careful. So take a second, get your 2 times. So if you are adding, looks like we get negative 0.04. And if you're subtracting, it looks like we get 5.04. And those units would be in seconds. So here again is where we have to think about what makes sense for the question. How long does the catcher have? It doesn't make sense to think of negative time. That would be before the ball is pitched. He already missed it. This is what we need. It'd be about 5 seconds. So being able to find how long is it in the air? How long does he have? Well, he has about 5 seconds to get there. So quadratic formula is a great way to find those zeros. All right, let's take it one step further just to get some applications. So how long will it take the ball to reach the maximum height? So when it's going up and then coming down, how long is it going to take to get there? Well, that's a time. That's like your x value. So the how long part is how long it takes to get up to this point at the top, which is the vertex. So do we have a way on our graphing calculator to find the vertex? Well, that's an absolute maximum, right? So we can go to our calculate menu on the calculator. We can find the absolute maximum. And we're going to get an ordered pair. What part of the ordered pair would be the time or the x? Well, that's the first one, so however long that takes. Then, could we figure out what is the maximum height the ball would reach? Well, sure thing. That means we just have to look at that same ordered pair, and we'd be looking at the y value. So the output is the height. So you could do it on your graphing calculator. You can find a max or a min point on the calculator and figure out those values. But we know we can do it algebraically as well. So you can complete the square on this guy and get it into vertex form, or there's a great little formula to find the x coordinate of a vertex. It's opposite of b over 2a is always the x. That comes from doing complete the square on that standard form equation. So if you can remember that, instead of using your graphing calculator and just kind of guesstimating on the calculator, you can actually calculate it by using this quick little formula, and you end up getting 2.5 seconds. Now let's see if you think that's reasonable. If it takes 5 seconds to get the whole way, seems pretty reasonable. It's going to take about 2.5 or half that time to get up to the top, because that other x-axis intercept was at just right before the y-axis. So that seems pretty reasonable. If it's in the seconds for about, or in the air for about 5, about 2.5. All right, now how would you figure out the maximum height then? If you know the x value is 2.5, how would you find the height, the y? Well, plug it in. So take your equation and plug in that 2.5 seconds and do that arithmetic. Be careful again. No mistyping and any good stuff, and you end up getting 103.5 feet. So the output, the maximum height, is almost 104 feet. Oops, that was 0.5, for the value of the maximum height. So it's a really interesting thing to be able to look at and understand that these parabolas have real life interpretations. The numbers mean something. So quadratic formula is a way that will solve any quadratic, no matter if they're real or imaginary. But remember, you can always try to factor first if that's easier.